Hello, my name is Samuel Lee. This is my Physics 2211 Lab Number 2, Projectile Motion. So to start with the introduction, I'll highlight the purpose of the lab and some of the fundamental physics principles present. The purpose of the lab is to explore the difference in an experimental model to computational model of the position of an object in projectile motion, which is affected by gravity. Drag was also considered in one of the two computational models. The computational model is based on fundamental physics principles and is used through GlowScript. This is important because it demonstrates the difference between something that's calculated and what will occur in a real-world situation. You'll also see that there's a large difference in the models when factoring in the drag force versus when ignoring it, especially when compared to the observational model, which will be explored later in the lab as well. Next up, I'll talk about the fundamental physics principles. So the first one is the position update formula, which helps to determine the position of an object after a certain amount of time given the average velocity and initial position of the object. You can see the formula below. Next, the velocity update formula helps you determine the velocity of an object after a certain amount of time given the terms shown in the equation. You need the initial velocity and the time, but also the acceleration of the object. However, using Newton's second law, which tells us that the net force of something is proportional to its acceleration and mass, we can substitute the net force divided by the mass for the acceleration, which is shown in the equation as well. Lastly, drag force is the final fundamental principle. Drag force is a resistance that is present when an object travels through a fluid, which could be water or even air, especially in this case where the force is air resistance. Drag force would equal negative b times the magnitude of velocity squared, and then multiplied by the unit vector velocity, where b is a constant. That way, this force is always in the opposite direction of the object's motion. So you know there's two models used, and the observational model is explained here. The system in this experiment was the wadded up paper ball, and the surroundings include everything around it, which includes the gravity from the earth and the drag force from the air. The paper was chosen as the model both for its simplicity and to make the shape as spherical as possible, in order to attempt to keep things like the drag force even across the sphere. This model also allows for an easy view of the path of the object, which is important when used to analyze in Tracker. You'll see an image of the trajectory of the object in Tracker and the data that it gave us. Next up, the computational models. So GlowScript was used to calculate and graph the movement of the objects. The initial parameters were determined from Tracker, and the velocity was calculated from the first few frames to the change in position and change in time. At the bottom of the slide, there's a screenshot of the initial parameters in the GlowScript code. Additionally, the computational model utilizes fundamental physics principles. The net force was calculated using the force of gravity, and that was added to the drag force. The net force was calculated by adding the gravity to the drag force, which the calculations are shown in the code on the right-hand side. The two update formulas are also on the same image on the right and was iterated for each time step in GlowScript. As for what the computational model yielded, you'll see the images of the no drag, the trajectory, and the blue arrow represents the force of gravity, and then with drag, with the coefficient of b equaling 0.1, the orange arrow represents the drag force. And here on the next one, the orange arrow also represents the drag force, but with the drag constant equals b equals 0.01. With this coefficient, the x distance traveled matched closest with the Tracker measured distance. However, the y value was off in both computational models when drag was assessed. Now that the models have been introduced, we'll go over the results. In our results, you'll notice a pretty significant difference in the different graphs of the position of the object. The different models are labeled on the graph, and what's most important is that you can see after adding in drag, the data wasn't closer to the original. The main reason for this was due to the fact that the initial velocity calculated from Tracker and subsequently used in the GlowScript code was most likely not accurate to the true velocity of the object, which is the dark blue line that follows. Also, by factoring in the drag force, it would cause the already not accurate GlowScript calculations to be even more off. And there's many potential sources of error in this lab. The first one is that during the throwing of the object, there could have been other forces acting on that changed it from the calculated model, which only used the force of gravity and the drag force. Secondly, there are potential human error mistakes during the coding part of GlowScript and the plotting of the object in Tracker. Ultimately, the sources of error coupled with the understanding behind the fundamental physics principles would account for the cause of the results shown here. Next up for the what if questions, and what does it mean? Would the time the object takes to reach the ground or floor be the same, longer, or shorter than the time it took in the original? You can see in the equation here the time would be shorter since there's no angle theta to account for when the object is thrown straight up. The equations here demonstrate this concept. Or in other words, having zero velocity in the x direction, the equation becomes just simply 2 v naught over g. And do any of your models predict the terminal velocity? And the answer is no. You can see that the velocity in the y direction versus time is not constant. The graph was similar enough for the model with and without drag. We can, in order to determine terminal velocity, we can design an experiment that calls for a much higher drop height, giving the object enough time to reach terminal velocity in comparison to this experiment. So overall, this lab looked at the differences in experimental and computational data and the change that factoring in drag force would cause in the plotted trajectories of an object. The results demonstrated a fairly visible or large difference in the three different models. Thank you.